Hi, everyone. So today, first, before I start, I want to thank Matt and Margarita very much for organizing this awesome symposium and for inviting me to present here. Also, I want to acknowledge the contribution of my collaborator, Rachel Heaton, with whom I worked on everything we'll be talking about today. So let's start with an observation. It appears that human cognition differs qualitatively from the sort of cognitive abilities of other primates, at least, and most other animals. Among other things, we use language, we develop mathematics and science and engineering, and for lack of a better word, we dominate the world as a result of this. And it's puzzling to wonder why. Why did it take evolution so long to stumble on what is obviously an extremely adaptive way of existing? And the explanation offered by Penn, Holyoak, and Povinelli, and among many others, or it's at least consistent with many others, is that the thing that makes us different is that we are capable of role-based relational reasoning, the kinds of things we talk about in this analogy seminar all the time. This is reasoning based on the roles to which things are bound, rather than just the literal features of those things. Another way to say this is to say, to make the heretical claim that human cognition is the product of a symbol system. We have mental representations that are capable of composing a finite number of elements into an unbounded number of expressions, where the meaning of an expression is a function of both the elements and their arrangement. So for instance, you can tell what's similar and what's different between the assertion the cat can sit on the person versus the person can sit on the cat. Okay. So this leads to some questions. Well, why? What are the computational requirements for achieving a symbol system? That is to say, how can a neural computing architecture give rise to one? And which of these requirements do people share with other animals, and which do they not? That is, what is or are the differences between the human cognitive architecture and other animal cognitive architectures? I'm going to make an assertion. Dynamic binding is necessary, but not sufficient for a symbol system. I've spent most of my career sort of arguing for this, and I'm not going to argue it anymore. I'm just going to assume it for the purposes of this talk. But I'll define it for you. What I mean by dynamic binding is binding neurons, representational elements, into groups on the fly and temporarily using some kind of external signal or tag that indicates how they go together. Most critically, the reason this kind of binding is necessary for a symbol system, I will assert, is because it does not alter the representation of the items so bound. So for instance, the same neurons can represent person, cat, and the can sit on relation in both the expression a cat can sit on a person and in the expression a person can sit on a cat. Okay. And one objection I always get when I make this assertion is, wait a minute though, but we know different, it means different, blah. Differences in the implications of these assertions, for example, who gets hurt, I will argue are the product of inference. They are not the product of differences in the mental representation of cat, person, and can sit on as a function of how they've been recombined. All right. Now, one of the claims I want to make today is that this kind of dynamic binding is necessary, but it's not sufficient to have a symbol system. It's necessary, among other things, because in order to have a symbol system at all, to represent relations among things explicitly, you've got to be able to segment the world into things that can be related to each other. For example, to think the thought that a cat can sit on a person, a computing architecture first must know that there's a cat and a person to enter into the relation. Crucially, holistic or, quote, entangled representations of the kind produced by deep neural networks are wholly unsuitable for this purpose. Dynamic binding is necessary for segmentation, I will argue, have argued before, and it's also necessary to bind relational roles to their arguments without changing the representation of either one. And it renders dynamic binding essential for generalization because it allows you to represent bindings without changing which neurons are involved. And this allows for generalization on steroids. It allows you to know, for example, that if P of X implies Q of X, regardless of what X is, then you can apply the rule P of X implies Q of X, if and only if you can represent P and Q independently of X. This ability to go from P of X to Q of X, I will argue, is precisely what a basic perceptual affordance is. So you see a surface, for instance, arrayed before you, and based on its properties, you infer that, I can step on that surface, or I can sit on that surface, or I can place my coffee cup on that surface, etc. Right? That's an inference of the P to Q form, where Q is the affordance. Now, what's interesting is that lots of animals can do this, not just people. Even cats can sit on surfaces they've never seen before. That is universal generalization of an affordance on the part of a cat. Okay. So, yes. So there's evidence that cats can do this kind of dynamic binding. There's behavioral and neurophysiological evidence that monkeys can do it. There's even neurophysiological evidence that insects can do it. The olfactory systems of fruit flies seem to do this. Now, what we've discovered computationally, based on a lot of models in the sort of connectionist tradition, is that this kind of binding can be rendered unnecessary if the modeler carefully segments the world into tasks and tasks into stimuli for her or his network. But out in the wild, biological organisms have to do this kind of segmentation and binding for themselves. Insects can do it by themselves without the help of a modeler. And this implies to me that insects are smarter than deep nets. But although binding is necessary for a simple system, it's not sufficient. Insects, cats, monkeys, and chimps have dynamic binding, but they don't have symbolic thought. So there's something else missing. Okay, but again, as I'll iterate a few times during this talk, dynamic binding is sufficient for generalizing universally from affordances. Okay, so once again, excuse me. All right, so going forward, I'm going to assume dynamic binding is a given in all the models I'm going to talk about. But I'm going to pose the question, what's missing from just dynamic binding? That is, what does a computing architecture have to add to the capacity for dynamic binding in order to accomplish a simple system, or Penn, Holyoak, and Povinelli's role-based relational reasoning? That is, what is the human brain doing differently than the brains of other great apes? The hypothesis I'm going to explore in this talk is that what we're doing differently is hierarchical integration. Our brains, but not other great ape brains, can integrate multiple role bindings into higher order structures to represent multi-place relations. That's one thing we're doing differently. The other thing we can do differently is that we can compute and learn mappings between systems of elements represented by such relations. That is to say, we can do analogical mapping. And important in this is also the capacity for copy with substitution and generation, although I'm not going to talk about that very much unless anyone asks about it in this discussion. So that's the hypothesis. Hierarchical integration is the difference. So the punchline, just to give it all away, is that if you have a system that can respond to its environment, then you have basic life. You've got viruses and bacteria and immune systems, and you've got epigenetics, and you've got simple machines such as thermostats. If you add to that a capacity for learning, then you get very simple animals like planaria, flatworms. You get immune systems, you get deep nets and recurrent neural nets. If you add to that capacity for dynamic binding, you get insects, birds, mammals, maybe fish and reptiles, I assume. You get animals capable of responding universally to basic affordances. That's non-trivial. Now, I should mention that recurrent neural networks flirt with solving the binding problem. They like try, but they don't make it. And so they remain in the lower right-hand box. But if you add to systems that can do dynamic binding a capacity for hierarchical integration of multiple bindings, then you get humans and possibly corvids, cetaceans, maybe elephants. You get symbol systems. The other punchline, the one that shows you how completely trivial everything I'm saying today is something that you'll all recognize immediately. What I've just said previously is equivalent to saying what dynamic binding gives you is combinatorics. It allows you to put known things into novel combinations or sets. This capacity is sufficient to do universal generalization of single place predicates, including affordances and egocentric relations, where the self is always the second argument of the relation. It allows you, if you can represent n items, it allows you to form the power set 2 to the n combinations or sets of those items. That's not too shabby. That's what dynamic binding gives you. But hierarchical integration gives you compositionality. It allows you to compose known things into larger relational structures, and that is sufficient for role-based relational reasoning, i.e. symbolic thought, especially when combined with the capacity for mapping and CWSG. If you have hierarchical integration, instead of 2 to the n combinations or sets, with n items, you can compose an infinity of expressions. So that's the hypothesis, that hierarchical integration is the shiznit that gives us this ability. And Rachel and I wanted to explore this hypothesis by laying out a space of models that do and do not satisfy these criteria and see what kinds of tasks they can perform. So we built 4 classes of models. The first thing we varied in building these models was whether the models were capable of system mapping. Some of them were not, and some of them are, that is to say, analogical mapping. The other variable we played with is whether the models were capable of representing multi-place relations. Some of them were not, and some of them were, okay? One of our hypotheses is that basic affordances reside in this cell of the matrix. As long as you're capable of doing binding, you can get basic perceptual affordances universally generalized with no multi-place relations and no capacity for system mapping. That's what I just said. This is what the neurons in the dorsal stream of your visual system are doing. They're telling you about your egocentric relations to other objects in the world so that you can interact with them motorically. Most non-human animals can do this. We've all witnessed they're capable of it. And any relations computed in this case, like people talk about the relations computed in parietal cortex, the egocentric relations between the self and the world, these are degenerate. They're not real relations because one of the arguments is always fixed to the self. So in other words, they can be simplified to single place relations, which is to say just rule bindings. They're not fully symbolic, I would argue. Another hypothesis is that symbol systems reside in the lower right corner of this matrix. And then an interesting question becomes, what the hell resides in the other 2 corners of it, if anything? Now, the modeling approach we're going to take to test this hypothesis is that we're going to run each kind of model, that is, models from each of these 4 cells, on each kind of tasks from each of these 4 cells. And we'll observe which models succeed and which fail on each task. Now, the hard part in doing simulations like this is to make sure that success or failure depends on the model architecture, that is to say, where it lives in this matrix, not on the semantic features we give it to play with. Okay, so just to elaborate that thought a little bit, this matrix specifies system architectures. That is to say, broad classes of computation that are within the system's reach, okay? The analysis I'm going to tell you about is completely agnostic about the specific representational vocabulary with which we're working, like whatever features, it's totally agnostic about that. It's important also to note that any computing system, even simple associative ones, can achieve almost any specific stimulus response mapping behavior if you train it on that mapping explicitly. So that's out of line. The question is therefore, what are the classes of computation an architecture can achieve without having prior experience with the specific mapping at hand? In other words, generalization is the whole game, okay? For example, can a system know whether it can sit on a surface that it's never seen before? And again, almost any architecture can succeed, can cheat, if you arm it with the right features. And so we're going to be very scrupulous about not doing that. And then I'll note finally, just as a technical point, all the simulations I'm going to tell you about were run using very old magic. This is the Hummel and Holyoak Lisa model from 2003. So no new technology here. All right, so let's look at the Nonocell, systems that are incapable of mapping and incapable of multi-place relations. These systems could do dynamic binding, but nothing else. All right, question is, can we use a system like this to infer basic affordances and bind them to completely novel objects, that is to say, generalize them universally? So that's the NoNo model, a model that has no capacity for mapping or multi-place relations. And the NoNo task is one that doesn't require mapping and doesn't require multi-place relations. And again, the example for this is a basic perceptual affordance, such as, can I sit on this? The way we're going to run these simulations is as follows. We're going to show the model two objects with collections of properties represented as predicates. And one of those collections of properties is going to be consistent with affording the action of sitting on, and the other one is not going to be. So there they are. The predicate properties of object one says these are the properties of object one. And this predicate properties object two says these are the properties of object two, where properties one of object, this version of properties, those properties applied to any x imply the affordance with respect to that x. Okay, so how do we represent this? Properties one is a predicate, which to begin with is just a vector of features. Think of them as neurons in ventral visual cortex. And what we're going to do with these features is we're going to bind them together dynamically by allowing them to fire in synchrony with each other. So they might be features like horizontal and flat and size greater than such and such, etc. Features that might tell a system or an organism that this surface is suitable for sitting. Okay. Importantly, these properties are invariant with each other. They're one way to call it is localist, right? They're independent of one another, and we assume they're independent of viewpoint and so forth. And for reasons we can go into in the discussion, this is made possible precisely by the fact that you're doing binding dynamically. Okay, whoops. Now, object one is likewise a vector of features, but these features just specify that it's an instance of an object in terms of its identity as an individual. That is to say, things that allow you to identify it as a token, where it is on the retina, where it is out in the world, etc. Okay. What we're going to do is we're going to bind the properties representing the predicate to the properties representing its argument, the object, dynamically by synchrony of firing. Okay. And then we're going to store those bindings into long-term memory using simple conjunctive coding. So we'll bind the properties that the features that constitute properties sub one by connecting them to a localist unit. And then we'll connect the features defining the object instance to a localist unit. And then finally, we'll bind these two localist units to a third localist unit that encodes the binding of the properties to the object. Okay. For those of you who are familiar at all with Lisa, you'll recognize that this is actually what we call a relational role. This is the argument to the role, and this unit represents the role binding. Okay. In earlier papers, this would be called an SP or an RB. So this is really old magic we're doing here. Now, what I'm going to argue is that this kind of representation, which represents a role binding explicitly, affords universal application of basic affordances, right? The basic idea is that the features of properties one activate another symmetric feature representing the affordance. You can sit on this. I'll go into the details in just a minute about how that happens. But since these features are bound to object one, and those features are bound to the affordance is now bound to object one, and the system as a whole knows that this surface can be sat on, or this object can be sat on. Okay, so returning to our example, what we're going to give the model as a perceptual input is properties one of object one and properties two of object two, and the target inference we're looking for it to make is that the affordance applies to object one. Okay. So in the perceptual representation, we give it these two simple objects and their properties, and then we give it one prior example in memory. This is the entirety of what this model knows. It's not been trained on millions or jillions of things. It's got actually two examples in long-term memory. Object 3 was bound to properties 3, and that included the affordance. And some other object 4 was bound to properties 4, and that didn't have the affordance. Okay. Now, properties 1 is going to share features with properties 3, and properties 2 is going to share features with properties 4. And as a control, objects 1 through 4 are otherwise identically similar to each other. So there's nothing about the objects themselves, aside from what's represented in the predicates, that can solve the task. Okay. So the idea is that when properties 1 becomes active in perception, it activates properties 3 in memory, and when properties 3 in memory fires, it fires in synchrony with object 1 and properties 1 in perception, activating the affordance. Okay, and the inference affordance is now bound to object 1. Okay, but when properties 2 of object 2 fires, it just activates properties 4 of object 4, and the affordance does not become active, and the model does not spuriously think that object 2 affords whatever action is afforded by the affordance. So there's no inference of an affordance. All right. So what does this really look like in terms of the network? Here are the units that were in the simulation. These are the properties, property 1 and property 2, object 1, object 2. In memory, here's property 3 and properties 4, object 3 and object 4. This is the affordance, and this is some other property that's not an affordance. When the system attends to properties 1 of object 1 over here in perception, it becomes active. Properties 1 becomes active, object 1 becomes active. They activate their respective features. These features of properties 1 activate properties 3 because they have similar features to each other, which activates properties 3 of object 3 and the affordance. Then object 3 becomes active, and that becomes active. The affordance is firing in synchrony with object 1, and the inference is complete. But when properties 2 of object 2 fires, that activates properties 4, which activates the non-affordance and object 4. So the inference is not made. All right. So this little model is making the correct inferences without any capacity for mapping and without any capacity for multi-place relations. These are just single place predicates containing properties. But because it can do binding dynamically, it can universally generalize its learning about the attributes of property 3 implying the affordance. And so the new object, object 1, which the model has never seen before, also gets the affordance inference. Okay. Now, it's one thing for me to tell you about all this, but we actually ran simulations, and to collect the data from these simulations, we stuck electrodes in certain units in the model to see which units fire with which other units under what circumstances. So we stuck an electrode that'll be plotted in red. I apologize, by the way, to all of you who are color anomalous. There's going to be red and green discrimination here. I'm sorry about that. But the object 1 was probed with an electrode will always depict in red. Object 2 was probed with a blue electrode, the affordance with a yellow electrode, and the non-affordance with a green one. And we're going to record the activity of these units during the simulation run to see who's synchronized with whom. All right. So this is the result of a run where the model first attended to properties 1 of object 1, and then it attended to properties 2 of object 2. And this is time on the x-axis and activation on those electrodes on the y-axis, where the orange or red is the critical object, the yellow is the affordance, the green is the non-critical object, and the blue is the, the green is the non-affordance and the blue is the non-critical object. So what we see here is, in very short order, the critical object, object 1, is bound to the affordance. The model has correctly inferred that I can sit on object 1. All right. But when we present it with object 2, it does not get bound to the affordance. It gets bound to the other property non-affordance. Okay. Now, lest you think this is a trivial accomplishment, this is universal generalization of an affordance to a novel situation, which depends on the independence of the affordance with predicate 3's other features, which in turn depends on the capacity to bind these features together dynamically. And as I intimated before, a fully distributed or entangled representation, as you would obtain from backpropagation, would not permit this generalization because things are not represented independently in a fully distributed entangled representation. That's precisely what entangled means. Everything is entangled with everything else. Okay. Now, and this is the easiest case we'll consider. We're going to move up the phylogenetic scale from here. Okay, let's consider the no-yes cell. So mapping is not permitted or required, but multi-place relations are. Oops. Okay. A system of this kind, architecture of this kind, is capable of dynamic binding, and it's capable of representing multi-place relations like larger than. But it's not capable of computing analogical mappings. So it should be sufficient for any kind of affordance that depends on a capacity to represent multi-place relations, but doesn't depend on a capacity to keep track of what corresponds to what against large systems. So that's the NoYes model. And the NoYes task, likewise, doesn't require mapping, but it does require multi-place relations. What would such a task look like? After having thought a while, Rachel and I came up with what amounts to a third-person perceptual affordance task. Something like, I can stack this on top of that, right? It's reasoning about a relation between two objects in the outside world. Those two objects are in some kind of relation, and the matching relation in long-term memory affords some action on one of the objects, whereas matching of the single place predicates that are similar to the roles of the relation does not afford that. So in other words, we're going to look at the model's ability to map object 1 and object 2 in some relation, relation A in perception, to map that relation to relation A prime in memory between some object X and some object Y. Now this notation where the X is red, what that means is that the relational role to which X is bound is the role that contains the affordance. That's what this will always mean. So when you see an argument showing up in red, that just means that argument is bound to the role that has the affordance. So we're going to look at the model's ability to map relation A onto relation A prime versus getting tempted to map the first role of relation A onto P1 and the second role of relation A onto P2. Okay, so in perception, we're going to just give the model two objects in relation A, and in memory, there's two objects, object 3 and object 4, in relation A prime, and two additional objects, objects 5 and 6, bound to predicates 1 and 2 respectively. Now, although relation A in perception is similar to relation A, shares some features with relation A in memory, each role of relation A shares even more features with these single place predicates. So this is a featural distractor that would throw a deep net off completely, right? That, that role 1 of relation A matches predicate 1 better than it matches role 1 of relation A prime. And role 2 of relation A matches predicate 2 better than it matches role 2 of relation A prime. So this is a genuine test of the model's ability to actually exploit multi-place relations as multi-place relations and distinguish them from just random collections of single place relations. In other words, it has to treat A and A prime as integrated wholes in order to get the correct inference. This is what the simulation looks like. Now, here's our old role binding units from the very first slide. Now, this is the first step into hierarchical integration. This unit integrates this role binding of A1, the first role of relation A to object 1, with this role binding, the second object to the second role of the relation. This unit integrates these two role bindings into a single assertion that relation A holds between object 1 and object 2. Okay, and then in memory, we've got an analogous structure for A prime and objects 3 and 4, and then single place predicates for objects 5 and 6. Okay. So if the model is tempted by a semantic match, then A1 will map to P1, and the model will fail to make the inference that the affordance goes with object 1. Okay, and likewise, it'll match A2 with P2, and once again fail to make the inference. By contrast, if the model can map A onto A prime, then it will map object 1 onto object 3 and make the affordance about object 1. Okay, that's what we're looking for in the simulations. Which of those does it do? And once again, we're going to sync the same 4 electrodes into the same 4 neurons. And this is the result. What we see here is that the critical object, object 1, is bound to the affordance by the second firing of the propositions. Okay, so when the first 2 rolls fire, this is object 1 bound to roll 1, and this is object 2 bound to roll 2. Nothing happens yet because of the dynamics in Lisa, but by the second firing of these rolls, the model already knows, okay, object 1 goes with object 3, and so it infers the affordance about object 1. Okay. Oops. All right, sorry. Sorry, I'm racing ahead, but that's because I'm trying to leave time for questions. Are there any clarification questions at this point, or are people doing okay? Cool. All right. Thanks, Matt. Let's consider now the yes-no cell. Think about a system that can do analogical mapping, but for some reason can't represent multi-place relations. It's of course capable of dynamic binding, but again, it's not capable of integrating those bindings into multi-place relations. A system of this kind would be sufficient to infer affordances based on distant object correspondences, but not based on multi-argument relations. Once again, it's difficult to imagine what that would ever mean, but we came up with something. That's what I just said. I apologize. The idea is this. You've got some property G of object A that maps to some property H prime of X, where H prime contains the affordance. But G of A doesn't map directly to H prime of X because G has nothing in common with H. Instead, the mapping of A onto X is mediated by a prior mapping of F of A onto F prime of X. What the hell? So that's what I mean by a distant correspondence. All right, so let's look at this in the abstract structure. We're going to tell the model that there exists an object A, which has some properties F, and A also has G, and B has properties H. In memory, we're going to tell it that F prime has X, G prime has Y, G prime of Y, and H prime of X again. So notice how the arrangement of the bindings of objects to roles is switched up in these situations. So based on F, we expect the model to map A to X. And then, oops. Now when G of A fires, G wants to map to G prime, so G of A wants to map to G prime of Y. But due to the prior mapping of F of A onto F of X, the system instead will map A onto X over here, therefore mapping G onto H prime and making the inference about object A. So concretely, a concrete example would be this. We let the model see that there's a large stick out in the world and it has a certain shape. And there's another stick that has another shape. And in memory, the system remembers once upon a time, it picked up, it saw a large stick, stick 3, and some other stick which had a similar shape to stick 1, but stick 3 had a different shape, but stick 3 had a different shape. Now, shape 2, well, where are we going? So what we're going to do is we're going to map large onto large so that stick 1 maps to stick 3. And although shape 1 is similar to shape 1, when shape 1 maps into memory, the prior mapping of stick 1 into stick 3 will cause shape 1 to map to shape 2, and shape 2 contains the affordance, this is a weapon. And so the monkey picks up shape 2. Okay, so this is what it looks like. I'm not going to drag you through it in gory detail because I hope you're getting used to that, but there's the way the model might misbehave and there's the way it might behave correctly. And this is what the simulation result looks like. So when we fire F of A, the affordance never becomes active because it's just not involved yet. But by the time we fire G of A, what we see is that object A is now firing in synchrony with the affordance because of the fact that the affordance is bound to H prime, whose correspondence to G is dictated by the correspondence between A and X. In other words, the model made an inference that could only have been made if it's capable of making a mapping and remembering it and using that mapping to constrain future mappings. And it did all this in spite of the fact that it still can't represent multi-place relations. So that's what a cognitive architecture that could do mapping but not do relations would look like. It's kind of smarter than the NoNo architecture, but it's weirdly smarter. Okay. Weirdest yet is the yes architecture, the one inside your brain. This one is capable of dynamic binding, is capable of system mapping, is capable of representing multi-place relations. Therefore, it's sufficient for full-blown analogy, full-blown symbolic thought, full-blown role-based relational reasoning. All right. So let's look at the yes task with a yes model. Okay, the yes task has to require both system mapping and multi-place relations in order to get the right answer. In other words, yeah, okay. So that the affordance has to be based on a full system understanding, right? To accomplish this, we're going to set up the following scenario. In perception, we tell the model relation F applies between objects A and B. Property G applies to A, property H applies to B. And in memory, some relation F prime applies to C and D. Some relation F double, or some property F double prime 1 applies to E, F double prime 2 applies to F, G prime applies to G. Finally, H prime applies to object C, which contains the affordance. Where? Based on perceptual similarity alone, what you would do is match H of B onto H prime of C, okay? And you would get the affordance wrong because the affordance really ought to apply to A, okay? And you would map G of A onto G prime of G, and that does not put the affordance on A either. And you would map F because you can't based on semantic similarity alone, you would map the roles of F onto F double prime 1 and 2, okay? But if you can represent multi-place relations, then you'll map F not onto F prime 1 and F prime 2, but instead onto F prime of CD. And if you can learn mappings, then having mapped F onto F prime, you will have mapped A onto C, and therefore you will map G of A onto H prime of C, and you'll get the affordance. I don't know whether we were able to come up with a concrete example of what this would actually look like in affordance land. Oh, we did. Consider encountering an abstract coffee maker that you've never seen before. And the first time you look at it, you say, what the hell? And then you scrutinize it a little bit and you notice a few relations. Oh, the tank feeds, this tank seems to feed the filter basket. And the tank has an open top and the filter basket also has an open top. And in memory, you're in mind of a regular coffee maker in which the tank feeds the filter basket as well. And the tank has an open top and the filter has an open top. And what you know is you have to put water into the tank. That's the affordance. The tank affords putting water in, and if you do that, coffee awaits. All right. So that's the concrete example of what we're doing if we are capable of symbolic thought. This is what it looks like with the single unit recording stuck in, with the electrode stuck in the right place. And what you can see is that Lisa has inferred that it must pour water into the top of the tank. Okay. The object, the crucial object A, is firing with the affordance. Okay. Here's our inference conclusion. The simulations suggest sufficiency, right? We built these cognitive architectures that we think ought to be capable of doing these things, hierarchical integration by building multi-place relations or by doing mapping. And we showed that tasks that require those capacities can be performed by these architectures. Not really very interesting, really. Kind of obvious. We designed it to, right? But what about necessity? That's in some ways the more interesting question. What happens if we try to give a task to a model that ought not be up to that task? In other words, a no-no model should fail on a yes-no task, a no-yes task, and a yes-yes task. And a yes-no model should fail on a no-yes model should fail on a yes-no task and a yes-yes task, etc. Right? So the simulation so far, if we break each of these squares down into subsquares to represent the tasks on which it succeeds and fails, where we represent success with green and failure with red, here's what we know. The NoNo model succeeds on the NoNo task. And we know the yes-yes model succeeds on the yes-yes task, and the yes-no model succeeds on the yes-no task, and the yes-yes model succeeds on the yes-yes task. That's sufficiency. But necessity should look like this. The no-no model should fail on anything except a no-no task. And the yes-no model should fail on the yes-yes task and the yes-no task. And likewise, the yes-no model should fail on these tasks and succeed on this one. And of course, the fully symbolic yes-yes model should find all the tasks easy. To give you the punchline, if I don't get time to show, I won't get time to show you all this in detail. This is exactly what happens. But some of the failures are really fun. So I hope to tell you, I'm going to try to tell you about at least a couple of them. All right. So let's look at the no-no model struggling to do the no-yes task. The system, again, is capable of dynamic binding, but nothing else. But the task requires multi-place relations. However, it doesn't require mapping. We predict failure. All right. This is where it gets fun. What is a no-no model and a no-yes task? This is a system, a cognitive architecture that can't form multi-place relations. But the task is one that can only be performed by a system that appreciates multi-place relations. Now, we realize there are at least two kinds of systems that cannot represent multi-place relations. One is like a Balint syndrome patient. This is a system that used to be able to form multi-place relations, but because of brain damage, no longer can. So it's got them in memory, but it can't perceive them, right? This is like, again, this is like Balint syndrome, which is, all right. So again, the model can't perceive relations, but it has them in memory. It's like an organism that used to be able to perceive relations. This will be a close control to the no-yes model on the no-yes task. The other version is something like more like a cat. This is a model that neither can perceive relations nor ever could perceive relations, and so it doesn't have any in memory. Okay. This is like an organism that's never known about spatial relations. This is a more fully non-relational organism. And again, in both versions of this, the task depends on relations. Okay, so in both of these cases, what we give perception is just F1 of A and F2 of B. Single place predicates because that's all the system can perceive. But this is our Balint patient. In memory, this system has a relation F prime of C and D. It's also got G prime of E and H prime of F. And as you can see, the first roll of F prime contains the affordance. Okay. And F1 is more similar to G prime than it is to the F1, the first roll of F prime, okay? And F2 is more similar to H than it is to the second roll of F prime, just as it was, this is the semantic similarity control we did in all the other simulations, okay? So semantic similarity favors the wrong inference as a control, but the relational structure favors the right inference. Question is, can the model exploit the relational structure to get the right inference? And the answer is no. Here are the standard electrodes. This is the critical object about which the affordance should be inferred. And here's the affordance. And as you can see, the model sort of thinks, oh, maybe the affordance, and it no, fuck it. And it goes with the non-affordance instead. All right. So it failed as expected. That was our Balint patient. That, by the way, constitutes a prediction, but one that we already know is true. Balint people can't perceive relations. All right. So for our cat simulation, what we have in memory is just F1 of C, F prime 1 of C, etc., where, once again, the similarity relations favor the wrong mapping, okay? But this time, we don't even embed these two into a common relation to help the system out. So we fully expect failure because the only thing to go on is semantic similarity, and that favors the wrong inference. And indeed, failure is what we get again, in the same way that we got it with our Balint patient. So I'm just going to show you the results. The no-no model also fails on the yes-no and yes-yes tasks. So this is failing on the yes-no task. It doesn't even come close to succeeding. And in fact, it binds the affordance to the wrong object on this task. And here it is failing on the yes, yes task, once again, binding the inference to the incorrect object. So it tries to act on the object that actually doesn't afford the action. Okay. So the next question I want to turn our attention to, and I've only got 10 minutes left, is the question of whether multiplace relations can obviate mapping. If you have one of these two almost there abilities, does that get you there? Can you fake it? And the answer is no. When I'm not going to tell you about the simulation details, but when you set up a simulation that gives multiplace relations the opportunity to obviate mapping, they can't do it, and the model makes the wrong inference. And then what about a yes-no model with a no-yes task? Can the capacity for mapping obviate multiplace relations? And that's the converse of the question we asked in the last simulation. And the answer is, once again, no, it cannot. Okay. Good. So the conclusion is this. This is what our matrix looks like. It looks exactly what you would expect it to look like. And right. These simulations support the conjecture that the way to get, or at least one way to get from a simple system that can universally generalize basic affordances from a system like that includes your house cat, to a system like Kurt Gödel that can prove the incompleteness of mathematical logic. The way to make that transition, according to these simulations, is to give the system the capacity to form multiplace relations and to give it the capacity to do system mapping. So in this square of the matrix is your cat and your frontal, your parietal lobes, right? And monkey parietal lobes. This is the kind of computation, according to these simulations, these are the kinds of computations that tell me how to pick up this seltzer can. Nothing fancy, but still fancier than most artificial neural networks. Whereas this cell of the matrix is fully symbolic cognition. Here's Kurt Gödel and your frontal lobes. And that raises the question, what are these two other cells? And a hypothesis is that these may be easier tasks, or it may be that a great deal of familiarity with tasks that used to occupy this cell of the matrix might allow them to move into one of these two simpler cells, right? These are hypotheses that Rachel and I haven't explored very systematically yet. Okay. So returning to the original question, how is human cognition different from that of other animals? The answer in general, as pointed out by Penn, Holyoak, and Povinelli, is that people are capable of role-based relational reasoning, that is to say, symbolic thought. The specific answer that I'm trying to suggest here is that non-human animals, most of them, are capable of dynamic binding and therefore capable of forming single place predicates, which allows universal generalization based on those predicates. But people are capable of integrating multiple such predicates into A, multiplace relations, and B, system mappings. And that renders the human cognitive architecture a symbol system. So returning to the punchline, dynamic binding gives you combinatorics. That ain't too shabby, but it ain't the same thing as compositionality. Hierarchical integration gives you compositionality. And this feels to me like a trivialization. I feel like I'm saying something that we already knew a long, long time ago. And yet it's so untrue of 99% of the models out there that purport to be trying to do analogy and other stuff. How did we forget? And let me give you one last caveat. I think this might be part of how we forgot. It's possible to cheat. A model with less than NoNo model capability can do anything you train it to do directly, even if you train it in a sneaky way, so sneaky that even you don't fully understand how the training works. DeepNet can be trained to compute any specific mapping. It's a lookup table. And you can do anything this way, but it would be idiotic to try. Even evolution is smarter than that. If you want to determine a system's true capacity, you have to test it on mappings on which it has never been directly trained, which is harder than it sounds, especially with the kinds of massive training sets that some of these deep net models are exposed to. But one question one way to start asking this question about any cognitive system, natural or artificial, is to ask, can it infer an affordance about an object that is truly and completely novel, that it has never seen before? Can it at least demonstrate universal inductive generalization based on single place predicates? And if it cannot, then that tells me it's not even as smart as a fruit fly. If you want to know whether it's really smart, well, then you can ask it to prove the incompleteness of second order logic without memorizing Kurt Gödel. Gödel did it, ergo, that's an existence proof the human mind can do it. I don't think there's any other model on Earth that can do it currently. And on that, I shall cede the floor to whoever has questions.